motors, parts for assemblies, just things, useful things, like Jonathan was saying in the previous video. So a lot of very typical types of CNC machining you'll hear in the industry are 3-axis, 4-axis, 5-axis. You'll hear the concept of multiple axes. So we want to quickly go over what that means. Basically, axes are planes of motion. So I think degrees of freedom is probably a better way to put it. Whereas if you have a 3-axis CNC mill, it means that it has the capability to move in three degrees of freedom. So for a 3-axis, typically that's X degree of freedom, Y degree of freedom, and then up and down are the Z degree of freedom, and they would call those 3 axes. And then there's actually a quick little GIF here, or GIF, to describe that. So this would be kind of your work holding fixture, that circular kind of piece, and then the what looks like a ant farm is your work, or your part that you're actually cutting a shape into. So this would be the part that you've designed that you want manufactured, and then the turning piece that's moving around is the tool. So the tool is moving very fast, right? Thousands of revolutions per minute, and then it's describing the 3 axes at which it can move. So what we kind of want to get across when we talk about this is the capabilities of this machine, so that when you're designing your parts, you're thinking ahead at what your machine is, what the machine is capable of, so you know how to design and how you shouldn't design, right? Like if you are just putting all these wacky features in there, and you expect this part to be manufactured using machining, or CNC machining especially, it has to be realistic to what your supplier or your prototype shop has in terms of machine capability. So if they tell you, if you know, 3-axis is the most common, I would say. So you can count on them having the capability to move and turn the tool like is being shown on the screen. If they don't, then I don't know what's going on. They probably can't help you. But yeah, you can count on them having this capability. As we sat down into 4 and 5, you may not be able to count on that, and that may rule out some of the more complex features that you were hoping to have on your part. Not necessarily rule them out, but just it means the complexity and the difficulty will increase by doing 4 or 5-axis typical features on a 3-axis machine. It means that they'll have to move the part to be able to reach different faces, and we can get more into that in a little bit as well. Anything you want to add, John, before we go on to 4-axis?
Yep. Yeah. And so one thought about just knowing the capabilities of the shops that you're working with is good, because then you can voice your part in those capabilities. And as in general, as Abel alluded to, the more setups, the more times they have to turn the part, the more times they have to touch the part, pull it off the machine and put it on, your accuracy goes down between those features, as well as the cost. And the cost goes up because more hands have to touch the parts. As well, for us in the medical area, often cost is second to time, and so time is the most important. Well, recently, lead times from suppliers are crazy, and so voicing your parts in the capabilities that these machine shops have will help get you quicker setups, faster machining times, as well as parts to you quicker. So design for manufacturability really is for minimizing cost, maximizing throughput, both in a production as well as a prototype environment. And so knowing the machines you're working with reduces those times.
Yeah, well said. As well, it increases your chances of getting the part that you originally designed on the first try.
Absolutely.
Not saying anything about, good or bad machinists. This is kind of like independent of that. It's your job as well as responsibility as the designer to to be anticipating that. You don't have to like pick, tool speeds and tool feeds for the machinist, because that's their job. What your job is to not make their life a living hell, right? Like that's
Right.
being a nice engineer and a nice designer.
Sure.
This is something that we didn't really learn in school. Is you learn in school that you just design what you need, right? And a lot of machinists are fine with that, and they're going to charge you that way. But they
Right.
really do appreciate when you have an idea of what you're asking for, and you understand what they have to do to get that done, as well as they really do appreciate when you show steps that you're taking to make their life just a little bit easier. It helps them be better at their job, and it makes you better at your job.
Yeah.
So
Cool.
moving on.
And one thought: if they don't have some of the capabilities that you need, specific to the machining environment, there are sort of brute force methods. Like if a feature isn't dovetailing with the 3 axes they have or the 4 axes they have, oftentimes they can sculpture mill or 3D mill or form mill a feature, but that's hugely expensive and time consuming on the machine as well as cost. So it just really, really benefits you to design for the tools that you have. But then the second thing is sometimes there are sort of brute force methods, and just use those extremely, extremely sparingly. Otherwise, the cost of your stuff is going to go through the roof. Okay, so 4-axis stuff, go for it.
I think it'll be a good time to talk about sculpture milling, 3D milling when we get to 4-axis, and then we can actually come back and touch on that.
Sure.
I'm really glad you brought
Great.
that up, because I forgot about that. So
good.
4-axis, as is shown on the screen, is typically accomplished with a sort of rotary fixture that's mounted to your 3-axis machine. So you see here that the tool is still moving in the same 3 axes that it was before, so the X, Y, and the Z axis. What's happening now is that the part is mounted perpendicularly to the cylinder that's now rotating in the A axis. This is not always the case, but you will have like a 4-axis capable mill where they've added a 4th axis to their vertical milling center, to the 3-axis milling center. And it allows you to do this. It allows you to, I think it says it here, index to different angles. If you're cutting something like, a hexagon feature into a circular part, you can index to those 6 spaces and just kind of mill that flat off. You can also do continuous, where you're actually cutting the entire time as the part is spinning, to do something like, let's say you wanted to cut a groove into your circular part, but not all the way around, like 3/4 of the way around, right? So that's how you would do something like that. This is also applicable to something called live tool turning. So if you have a turning center or a lathe and with tools that can spin independently, and that's a little bit more in depth than I kind of want to get in this first video, so we can cover that, but that is not the only case that this happens. There are a couple of different cases where you can expect 4-axis capability. And this, I would say, for what we do, Jonathan, is almost standard, would you say?
Yep.
To have 4-axis capability? Because it's like you have 3-axis capable stuff, like things that you can make in 3 axes is like kind of down here. But then as soon as you say, oh, I have 4-axis capability, it skyrockets. You can make so much more stuff. And then I don't even know if it skyrockets again for 5-axis. Do you think? There's a niche of things that you need 5 axes to make, but you can simulate them. You can simulate 5 axes with less axes. But then also, it's not very common that you need a 5-axis setup to make a part. Would you agree with that?
Yep. Okay. Yeah. Yep.
Like Jonathan said, as you can imagine, rotating the part just allows you to reach many more faces, like, obviously infinite angles around the part. Whether or not you want to utilize infinite angles is another question, of course. But but imagine, you have this setup, right? A 3-axis setup, but you wanted to add a sloped face. Like Jonathan said, if that slope or curvature, if you want to mimic that, there is that technique called sculpture milling where your tool can still move in the X, Y, and Z, and you can imagine that you can just draw curves with that tool along those 3 axes. So you're making, parabolas or arcs in 3D space instead of just traveling along a straight line all the time.
Right.
You need a different.
So combining a move both in the X, Y, and Z axis can give you some pretty funky curves.
Yeah.
Yeah.
Again, you need. You can really only do that with round tipped end mills or ball end mills, because again, since you're combining motion, that may be a little bit more in depth, but you need special tools to do that, and it takes much longer because you're actually cutting a very small amount of material away at a time. You can't just take big swaths of material away as you cut. You're using less of the tool, I guess I should say.
Yep.
Anything else you want to add on that note?
No, but sorry, and I want to drive home what Abel said as well. As soon as you add that A axis, that 4th axis, it really opens up. It makes a lot of stuff possible, and even on really crappy CNC machines, if you don't have to reset the part up, there's some asterisks to this, but if you don't have to reset the part up, often it's very, very accurate. So what a 4th axis allows you to do is reach 4 faces in one setup so that they don't have to take it out, put it back in, and now everything is going to be pretty accurate to the other features.
Yep. So even if you don't need that circular capability, it still saves you the setup versus a 3 axis.
Yep. Yeah. To get to the 90-degree side or to get to the opposite side. Absolutely. Yep.
Okay, cool. Let's quickly talk about 5-axis, and if you've seen machining videos, it's probably going to be something that looks like what's on the screen now.
Right.
Which is just,
right.
Crazy, compressor.
We've all seen those videos. Let's be honest. Yeah.
Compressor wheel, like just crazy stuff. Everything's moving at the same time, and that's pretty much what 5-axis is, right? So there's hardly a nook or a cranny that you can't reach with a small enough tool and with a certain angulation of B and C axes, as well as moving the tool again in the X, Y, and Z. There are a couple different styles of 5-axis machines, but they work essentially the same way. They can reach mostly identical areas. So 5-axis stuff can be extremely difficult to program and very expensive to do. So I think the point we're trying to drive home with this is that 5-axis can pretty much do everything. Like, there isn't a lot of stuff that you're gonna come up with unless it's weird, wonky internal features. If it's an external feature part like you're seeing on the screen, regardless of the curvature, regardless of weird angles that you put in the part, you can do it with 5-axis. You don't want to play that card all the time because there aren't a lot of shops with that capability. Mostly big shops will 100% have this capability, but even then the work area is very, very small, much more limited in terms of the size of your parts. It's much more difficult to program, and it's also much more expensive just in that time. The time it takes to program, the time it takes to set up, the time it takes to cut. So you don't want to play that card a lot. It's kind of your trump card, But yeah, it's there if you need it. I think the point we're trying to drive home is that you want to use, and that's the point that this drives home to this article, is that so you want to choose 3-axis as often as you can. When you know that you can't, you can rely on having a 4th axis. When you can't do that, you can plan to use a 5th axis. But just, I think the underlying point is that just know what you're asking for, right? So this is just kind of a 10,000 foot overview, introducing you to the broad world that is CNC machining, and we haven't even scratched the surface. And there are probably going to be some machinists that comment and call us both idiots, which is totally true. We're not going to deny it. But from our perspective, from our experience in the workplace, and that's 4 years from me, and Jonathan's got 18 years.
Yep.
So from
something
our
like that.
This is what's useful as a design engineer in I guess medical device currently to understand and to be thinking about, because you'd be surprised with how little they kind of drive this stuff home in university and in college. Just what's useful to know about what happens on the shop floor. You don't need to know everything. That's not your job. But it is useful to know some things. So I think I think that's it for me. Anything you want to add in closing?
No, I think that looks good.
All right, awesome. Well, I think that's it for today. I think we're good to cut the stream. Thank you to those that are watching either on the stream or on YouTube after the fact. Yeah. Well,
all those bots watching right now.
That's right. I don't know. What do you think we'll cover next time, Jonathan? Do you have other topic ideas already, or?
I want to, or let's cover designing the same part in a couple different CAD environments. So, I'll show Creo and SolidWorks, and you can show
Fusion. Yeah.
Fusion 360.
Yeah. So we'll do like a Reddit design challenge or something like that from r/CAD. We'll pick apart, or it may be that, or it may be something that Jonathan wants to do, and we'll step through that together, whether that's just the design or possibly even drawings in another episode. Sound good?
Yeah. Sounds awesome.
Okay, and then join our Discord and subscribe to our YouTube channel, and those will be linked in the channel page, I think. Yeah, and we'll make announcements there.
Yep.
All right.
Awesome.
Thanks, everyone. Thanks for watching.
Thanks.
See you next time.
Talk to you guys later. Bye.